All right, guys, looking at the last lesson then for chapter 9 today. Talking about the last remaining things about correlation, regression, the scatter plots, and the line of best fit. All right, so today we're talking about, I got to focus that thing. That's pretty bad. That's over here. Turn the light on, see if that helps. Yeah, there we go. That looks a little better. Okay, so today we're talking about the explained and the unexplained variation for linear regression. All right, so what it's talking about as far as variation is that the predicted value is not always the same as the actual value, which kind of makes sense. That predicted value is more of an average, right? So half the time, right, we're going to be on one side or the other of it, and it's not always going to be right on. So it's like an average, and the actual values that occur are going to be near there, right? So that's it's just a prediction, right? And in these days, we know predictions are not necessarily always true. Okay, so we have a new name, the coefficient of determination, all right, and that's the name for r squared. All right, so R is a correlation coefficient, R squared is the coefficient of determination, right? So the variation discussed in this topic is the difference between the predicted values from part D and the actual values that occur. Okay, so the explained variation expressed as a percent is R squared. The unexplained variation, too easy for you to say, expressed as a percent is 1 minus r squared. Okay, so example. If the correlation coefficient r for a set of bivariate data is 0.905, so if r is 0.905, right, then r squared is really just 0.905 times 0.905. Right, so 0.819025. Calculate the explained and the unexplained variation from this data set. Okay, so the explained is r squared, which is 81.903%. All right, and then the unexplained, 1 minus r squared, I'm just going to take 100 and subtract the 81.903. And I get 18.097%. Okay. Hopefully that's a pretty easy topic. Hopefully most of chapter 9 has been pretty easy and straightforward. All right, so one more thing that we have to do, and that's called graphing the residuals. All right, so the residuals are the same thing we've been talking about. It's the difference, right, between the predicted value, right, and the actual values. All right, so in our work here, we have an equation for the line of best fit, and that's y hat equals 22.361 plus 1.599x. Right? Linear regression gave us a line of best fit from this data. So I didn't change the data on you. This should still be in your calculator. All right, so stat edit. Let's see how many different things I used this for. Oh, nope, those look pretty good. All right, so all right, my data. Let me hit that focus again because that looks really bad. And all right, well, that's a little bit better. Okay, so the next column I need is y hat. So that's the predictor So that would be taking each of these x's, putting them in the equation for x, and then putting the result here, right? And the nice thing with these calculators is that it will do that for you. All right, so I went up to the title and I did 22.361 plus 1.599 times x, and my x's are in list 1, so I do times second 1, enter. All right, so all of these numbers are my predicted value. 70.331, 76.727, 65.534, 62.336, 49.544, 59.138, and 54.341. Okay, so y hat, those are my predicted values. Now the next column is y minus y hat, all right? My y's are in list 2, my y hats are in list 3. So if I go to the next column, go up to the title, I'm going to do L2, second 2 minus second 3. L2 minus L3, boom, there's all my differences. Okay, so negative 4.331, 2.273, 4.466. All right, and again, this is 70 minus 65.534. Negative 2.336, negative 1.544, negative 4.138, and 5.659. All right, so coming up with the data, all right, is not that big a deal when we have the calculator to work with. All right, so when we graph those residuals, all right, I'm going to have 0 in the middle. And as I look at the numbers, the highest is 5.659 and the lowest is negative 4.331. All right, so if I go up to 6 and down to negative 6, that will take into account all of those numbers. All right, so the first number is negative 4.331. So there's my 0. It's going to be somewhere down here. My second number is 2.273. So I just move over a little bit. 2.273 isn't as high as 3. All right, and then 4.466. All right, so I move over a little bit. Move over a little bit, negative 2.336. Negative 1.544. Negative 4.138. And again, guys, when you're getting these dots, it's just a ballpark figure. You don't, or spot. You don't. I'm not going to measure to make sure you had it perfectly right. But ballpark is close enough. 5.659. That was my highest. So my last one's going to go here. All right. So what you want to occur here is this needs to be scattered all over the place. All right. If you have a pattern, say, that looks like a parabola, right? So they start out high, end up really low, and then come back high again on the other end. All right, that's a problem. And what it means is there's probably another regression that would have worked better, right? And that parabola could open down in 2, all right, that would still be a problem. But these are all over the place, and they're really, if you're talking numbers around 60 and 70, and our highest difference is less than 6, then that's not too bad. All right. So this is a pretty good a pretty good graph. And what it says is that the linear model is a good fit. Okay. All right. So that is it, guys, for chapter 9. I saved the shortest for last. And hopefully this will be pretty easy for you. I will get an assignment up for you to do on this chapter. And you can finish that up and attach it back to Blackboard. All right. Have a great day. Good luck. I always like to say you don't need luck when you're good. But anyway, good luck, and we'll see you next time. Bye.